Cactus shipped a language model that fits in 14 megabytes and it refuses to answer you in words. Needle 2 is Cactus Compute's open tool calling model, and the spec sheet reads like a typo. 45 million parameters. One file. A whole session that sits around 28 megabytes of RAM. The repo is at roughly 4,000 stars. The license depends on which page you open. GitHub shows MIT, while the launch page and the model card both say Apache. And Cactus says the thing runs on a Raspberry Pi, a cheap Android phone, and microcontrollers with a little external memory. Enjoying this so far? Subscribe to the YouTube channel and grab the free daily newsletter at indiehacker.news. New deep dive every weekday. Start at the top of the README and the pitch is one line: tool calling, device use, structured extraction. Scroll a little and you hit the install. A single pip line with a note that the engine gets pulled from Hugging Face once and cached after that. Keep going and the attention section arrives, the part that explains why your tools can never be evicted by a long conversation. Below it sits the routing rule for declaring more tools than the model will hold, and how it scores each schema. Further down, the confidence field, which is the one that decides whether you can ship this at all. And the last stretch is fine-tuning, which runs on the machine already in front of you. Every model on the comparison sheet is bigger than this one. FunctionGemma at 270 million parameters. LFM 2.5 at 230 million. Apple's foundation model at roughly 3 billion. Cactus puts Needle at 5 to 70 times smaller than that field, running at 2 bits while the baselines run at F16. The training gap is wider still. Needle saw 115 billion tokens of pre-training and 38 billion after it. Cactus says LFM 2.5 saw 19 trillion, about 120 times Needle's total. The speed numbers all come off cheap hardware. Prefill on a Raspberry Pi 5, decode on the same board, then sub $200 phones, and the compute cost of a single token. The scoreboard splits by benchmark. On seal tools, where the model has to pick the right tool from a declared set, Needle leads its class both in and out of domain, and the harder split holds back entire tool families it never saw in training. On Google's mobile action set, it lands third of 4, but its function name accuracy is the highest in the group at 98.3. On Droid Call, which is Android intent style calls, it lands at 17 against FunctionGemma's 17.5, and all three score 0 on the rows that need 2 calls in a row. Want to be featured? Pitch your open source repo at indiehacker.news/apply and get in front of thousands of builders. Start with what comes out of it, because that is the strange part. Needle has no free text path at all. Every request gets answered as a function call, and when it cannot serve you, what comes back is the empty call, an open bracket and a close bracket, nothing else. Structured extraction runs through the same door. You declare one tool, the model fills that schema, and conformance is guaranteed instead of requested. Arguments only carry values the input evidenced, so an optional field with nothing behind it gets left out rather than invented. Then the confidence number, which is the smaller of 2 signals, a calibrated head scoring the full prompt plus the call it produced, and the raw probability of the call tokens. Both have to agree before the call is accepted. The sample response in the README shows the shape, a confidence of 0.94, a prefill rate, a decode rate, a peak memory reading. Those throughput figures name no device, and Cactus never presents them as a benchmark, so read them as an example. Now the runtime, which is where the memory ceiling comes from. Attention runs on a sliding window of 256 tokens, and your system prompt plus your tool declarations get pinned in as permanent sinks. So the tools can never fall out of context and total memory stays flat no matter how long the session runs. That flat ceiling is the whole microcontroller argument. Cactus lists parts like the ESP32 P4 with 32 megabytes of external RAM and ships the engine as a static library for Cortex M4, M7, and M55. Tool routing is capped too. 5 or fewer declared tools go straight into context. Past that, a retrieval head embeds every schema once at startup, scores your query each turn, and admits only the top 5, so an unselected tool becomes unreachable rather than unlikely. The architecture has a name and a paper behind it, Simple Attention Network. 27 layers, 512 wide, with a Hadamard MLP, where the feed-forward block usually sits, grouped query attention, and multi-lane hyperconnections. 8 of the 45 million parameters live in the n-gram, read by a gather and costing no arithmetic, which is why only 35 million of them are Matmul active. The 2-bit compression is trained in rather than bolted on afterward, from pre-training through post-training across weights, activations, and the KV cache. And the paper is what makes the shape defensible. Delete the feed-forward layers on their own and you lose 0.47 nats. Spend that budget on attention depth instead, and the gap closes to 0.006 nats at matched parameters. Install is 1 pip line, and the promise on the page is that there is nothing else to build. The engine gets pulled from Hugging Face once, stays cached, and inference after that touches no network. If you want to teach it your own tools, the synthetic data generator is a second command, and it is the only step in the loop that calls somebody else's API. The repo is moving daily. The newest commit at Capture is dated August 11th, 2026, and it covers release workflow and version handling. The playground landed the day before, server and interface both, and it runs locally with preset tools and a button that retrains on them. The day before that, the architecture assets. The release folders tell you who this is aimed at. Pre-built binaries for macOS, Linux, Windows, Android, and iOS, plus RISC-V, ARM-v7, and MIPS32 for camera and router chips. There is a WebAssembly build too. 9 contributors are carrying the whole thing. The limits are real, and BFCL version 4 is where they show. Needle finishes last of 4 there, 42.6 against Apple's 61.7, and Cactus points at Java, JavaScript, and the parallel call categories, none of which look anything like a phone. Second caveat, every accuracy and speed figure in this story was published by Cactus itself, and the baselines ran at full context under VLLM, while Needle ran end-to-end through its shipped binary. Third, the only named product running it so far is Pebble's Index 01 app. So treat this as a component for a fixed set of device functions, benchmark your own tool schemas before you build on it, and the full write-up is at indiehacker.news.